So in this subset, we are going to look at balancing combustion reactions, and specifically we're going to look at balancing combustion reactions of hydrocarbons. So let's go through the steps first, and then we'll have a look at some examples. The first step we want is to write out the skeleton chemical equation, and I'll show you what that looks like in a second. The second step is then to balance everything, so balance all atoms except for carbon, hydrogen, and oxygen. Okay, you need to leave CH and O until last. Third step is to balance carbon. Fourth step is to balance hydrogen, and the fifth step is to balance oxygen. Okay, now I've written them out as 3 separate steps, but you could also just think about balancing these guys in alphabetical order. Okay, so carbons, then hydrogens, then oxygens, and this sequence of steps works for pretty much every type of hydrocarbon combustion reaction. You just got to make sure that you get your maths right. Okay, so we'll have a look at some examples in a sec. So first of all, let's have a look at what I mean by skeleton chemical equation. I'm essentially talking about some sort of hydrocarbon, which is that CXHY, okay, because obviously a hydrocarbon has some amount of carbon and some amount of hydrogen. Okay, we're reacting that with oxygen, O2, and that's always going to produce carbon dioxide and water. So let's have a look at some examples now. So let's go orange. So e.g., let's say that we've got methane. Okay, methane, the simplest hydrocarbon. So methane is CH4. Okay, let's say we want to write a balanced combustion reaction equation for methane, and let's just follow the steps. So the first step is to write out the skeleton equation. Okay, so we've got CH4, we're going to react that with O2 gas. That's going to produce carbon dioxide and water, H2O. Okay, first step done. Second step is to balance everything that's not CH or O. Now, in this case, we only have CH and O, so we can go straight to step 3. Step 3 is to balance carbon. Okay, so if we have a look, we have 1 carbon on the left and we have 1 carbon on the right, so our carbons are balanced. Now, sometimes people like to do a little table kind of thing down the middle. So they like to do this, so you can sort of just tally up how many of each atom you have on each side of the equation. So if we have a look here, on the left we had 1 carbon and on the right we had 1 carbon, so we are balanced on that one. Okay, if we move to step 4 now, balance the hydrogens, we have 4 hydrogens on the left and we only have 2 on the right. Okay, so the way that we are going to fix that is we are going to put a 2 in front of the H2O on the right. Okay, so we now have 2 times 2, which is 4 hydrogens on the right. So let's change that to a 4. So it's always a good idea to do this in pencil when you're doing this on paper. Okay, the last step is to balance the oxygen atoms. All right, so now if we have a look on the left, we have 2 oxygens. Okay, and on the right we have 2 oxygens there plus another 2 oxygens, so a total of 4 oxygens. Okay, so to fix that, we are going to put a 2 in front of O2 on the left, and now we are balanced. Okay, and if you want to, you can do a little check at the end to make sure that you have the right numbers of atoms here. Let's look at another example now. Okay, let's go for something a little bit spicier. Okay, so example 2, let's say we have this guy. So we've got C8H, let's go C8H18. Okay, so that is octane. And let's write a balanced combustion reaction equation for the combustion of octane. So the first step is to write out the skeleton equation. So we're going to combine our hydrocarbon with oxygen gas, and that's going to produce carbon dioxide and H2O. All right, and it's always a good idea to leave a little bit of room between each of your species here. Okay, so that's the first step done. The second step is to balance everything except CH and O. again, we don't have anything except for CH and O, so we'll go straight to step 3, which is to balance CH and O, starting with C. We want to go in alphabetical order. So again, I'm going to do a little table down the middle because I find that helps people. Alright, so CH and O. Alright, and let's keep track. So on the left for carbons we have 8, and on the right we just have 1. Okay, so the way that we are going to fix that is we are going to put an 8 in front of the CO2 on the right, and again I'll just go back to that purpley color. Okay, so an 8 in front of the CO2 on the right, and now we have 8 carbons on the left and 8 on the right. Okay, so let's go to the next step, which is to balance the H's. We have 18 on the left. Okay, so 18 on the left, and we only have 2 on the right, so we need to fix that by putting a 9 in front of H2O. Okay, so 2 times 9 gives us 18. So we now have, and again, I'm going to try and keep those colors the same, 9, okay, and we now have 18 hydrogens on the left and on the right. All right, so let's look at the last example. Sorry, not the last example, the last atom here. So we have 2 oxygens on the left. Okay, 2 on the left, and we have, now we've got to be careful here with our arithmetic, okay, so we've got 8 times 2, which is 16, plus 9 times 1, which is 9, so 16 plus 9 gives us a total of 25 oxygens on the right. Okay, so that is definitely not balanced. We've got 2 oxygens on the left, 25 on the right. So the way that we're going to fix that is we're actually going to do a little bit of algebra to work out what the coefficient of oxygen should be. So the way I like to think about that is we're going to need some coefficient of oxygen, O2, let's call it X, okay, and we know that there's 2 oxygens on the left, so it's 2 lots of whatever the coefficient of the oxygen will be, has to equal 25, okay, because we want to have the same number of oxygens on the left as we do on the right. Okay, so now it's just a little algebra equation that we can do. It's really straightforward. So if we divide both sides by 2, we then have on the left, the 2's will cancel out and we just get an X, and on the right we have 25 over 2. So that means that the coefficient of oxygen, of O2 that we need, is 25 over 2. Alright, and that's okay. You know, some people get a little bit put off when you see a fraction, but it's alright because fractions are still numbers, and when you get to stoichiometry, you'll learn that we're not talking in terms of entire molecules, we're talking in terms of ratios here, okay? So these coefficients actually represent ratios of these molecules. Sometimes, it's worth mentioning that sometimes in some texts you will see that they will double all of the species here. So they'll double the coefficients on all of these things. So instead of just having, you know, C8H18 and 25 over 2 and 8 and 9, they'll actually double all of those coefficients. So what they'll actually end up with is a 2 in front of, and I'll just try and that's, there we go. So we'll put it 2 in front of this. Okay, so 2 C8H18. If we double 25 over 2, we end up with just 25. That produces 16 CO2 and 18 H2O. And again, it's perfectly valid to do it this way as well. It's perfectly fine. Some people actually prefer this because it has no fractions. But remember what I just said before, that these coefficients represent ratios, okay? We're talking about ratios of molecules here. I'll move this over a little bit where it's less crowded when it decides to work. There we go. Okay, so we're talking about ratios here, so it actually doesn't matter whether we have these whole numbers or whether we have a fraction in there. It represents the same thing, okay? What is important is that we balance these things correctly. So let's look at one more example, and I'll give you a chance to pause the video and have a go at this one yourself. So for this example, let's say that we want to balance this hydrocarbon, and sometimes, you know, you're not going to get a nice alkane like the methane or octane that we just looked at. Sometimes you might get one that's a little bit funky. So let's have a look at an example of that. So let's say we've got C6H6, okay, and I want you to pause the video and have a go at writing a balanced chemical equation for this. Okay, so let's have a look at how we will do that. So again, first step is always to write out the skeleton chemical equation. So we're going to add oxygen gas. It's going to produce CO2 and H2O like that. Okay, then we want to balance our C's, H's and O's in that order, seeing as we don't have any atoms that aren't CH or O. So let's do our little table down the middle. CHO like this. Okay, so on the left we have 6 carbons. On the right we only have 1 carbon. Okay, so we are going to fix that by putting a 6 in front of CO2. Okay, 6 there. Then on the left, if we move on to hydrogens, we have 6 hydrogens on the left, and we only have 2 on the right. So we've got a 2 there. So to balance that, we need to put a 3 in front of the H2O on the right. Okay, because now 3 times 2 gives us 6 hydrogens on the right. And I should be updating these as I go. I want to go back to that green. Here we go, 6 and 6. Cool, so carbons and hydrogens are balanced. Now we want to go to oxygens. So on the left we have 2 oxygens, and on the right we have 6 times 2, which is 12, plus 3 times 1, which is 3, making a total of 15 oxygens. Whoops, didn't mean to get rid of that. Okay, 15 oxygens on the right in total. So to balance that out, we need, and you can do your little algebra equation like we did before. You can do 2, not G, don't know where that came from. Get rid of that one. Okay, 2 times by the coefficient of oxygen has to equal 15, and if you rearrange that you will get x equals 15 over 2. Okay, so again a fraction coefficient, and that's okay. That's okay because it represents the ratio. Alright, now if you wanted to double everything so that you don't have that fraction, that's also perfectly fine. So I'll show you what that would look like. You would end up with 2 lots of C6H6 plus 15O2 produces 12 CO2 and 6 H2O. So that is also an equivalently balanced chemical reaction for that combustion. And there you go. So as long as you follow the steps that we talked about above, okay, so write out the skeleton chemical equation, balance everything except CH and O. That's only really if you get any funky looking hydrocarbons that they might have like a nitrogen or a sulfur in there as well. Okay, and then you want to balance CH and O in order. If you follow those steps, you will always be successful in balancing combustion reactions of hydrocarbons.